Very happy to have Professor Kamien from University of Pennsylvania giving a talk on new classification of topological defects. Randy, to you.
Great, thank you. I've been attending your seminars. These seminars, they're great seminars, and I'm glad that I have a chance to speak because I feel that there are people on the other end of this line who might be able to answer questions that I have, and so we'll get to them by the end. This is work that I did. Some of this is work that I did in collaboration with Hillel Aharoni, Yi-Chen Hu, and Tom Michon. So before I begin and showing you mathematics, let me show you, right, for the the uninitiated, let me show you some topological defects. So when people study liquid crystals, pneumatic liquid crystals, you put them through cross polarizers and you see these incredible images. And I'm going to explain all the parts as we go along. So you notice something when you see these black lines, which is sometimes the black lines come together in fours, groups of four, and there's some sort of thing going on. And actually, sometimes they come together in groups of two. That's going to play an important role later. Okay. So what are you seeing? What's the experiment? So there's a backlight, there's a polarizer, and there's another polarizer which we call the analyzer so that we don't confuse ourselves, right? Polarizer and analyzer, two different things. Now, if you send light through a polarizer that's polarized vertically, and you then analyze it with a polarizer that's horizontal, usually you get black. But in between these two plates is some liquid crystal. And these liquid crystal molecules are long molecules. They have an anisotropy that is both geometric, and they also have an anisotropy that's optical. And because of the optical anisotropy, what happens is when you send polarized light in that's polarized this way, it hits the molecules and it actually gets rotated a little bit. It becomes elliptically polarized. And so actually you get a signal. A signal comes out. And that's what you see down here. You see the light. And then you say, why do you see black? I thought you said that there was always a signal. Well, if it turns out that the molecules are oriented, happen to be oriented, so that the molecule is parallel to the polarizer, if the molecules are parallel to the polarizer in any particular region, then the light that comes in only sees one of the axes of the molecule. It doesn't see both axes. It doesn't decompose, right? So if the light were polarized like this and the molecule were at an angle, then when you decompose along the two axes of the molecule, you get a projection. But if the molecules happen to be along the polarizer, only one way for the light to propagate, only one dielectric constant. And so, in fact, the light goes straight across and stays polarized in the vertical direction. Likewise, if the molecules happen to be aligned along the analyzer, then whatever happens as the light goes through the polarizer, it comes in like this, and it only, again, sees one projection of the molecule's axes. And again, you get black. So the black here corresponds to the pre-image. It's the pre-image of these two directions. All right? If the molecules happen to be pointing up and down or left and right, then you get black. Otherwise, you get color. And that's the important thing. All right? So, in fact, it's nice. This thing already gives you topological information. And then you say, well, what's happening at these interesting vertices? Well, at these vertices, what's happening is there's a place where the molecular orientation isn't defined. So here I'm drawing some lines. What would the polarizer and the analyzer do? Well, the polarizer says any time that you have molecules that are parallel to the polarizer, you should get black, which you do. And the analyzer tells you, oh, well, whenever the molecules are parallel to the analyzer, I should get black. So if I do that for all four of these things, what do you see? You see that in all four cases, you get these four brushes. And what's happening? Why do you get four brushes? You get 4 brushes because you go through the polarizer direction once, and then the analyzer direction, and then the polarizer, and then the analyzer. All of these configurations that I'm showing here are things that vector fields could have, right? So these can all be oriented, except at the place where there's a defect. And because they can be oriented, they have to go around by 2 pi. So when the molecule direction goes around by 2 pi, it goes through the polarizer twice and the analyzer twice, and that's why you see 4 black lines. And then if you remember what I showed you that in fact, sometimes you only get 2. What that means is that in fact, these things aren't vectors, they're actually an aligned field. So in a liquid crystal, just as the rods, you can see a rod like this, a rod actually generates a line field, not a vector field. And so, in fact, this tells you that the configuration space of the molecules is not the circle, but in fact, it's RP1. Okay. So, let me show you how these defects behave. One of the weird things about the defects is here you have 4 brushes, and here you have 4 brushes coming out. So you know that this wraps around by 2 pi, and this wraps around by 2 pi, because they both go through the polarizer twice and the analyzer twice. But you don't know in which orientation, right? So when you talk about the zero of a vector field, the zero of a vector field can either be +1 or -1. Do you rotate around by +2 pi or -2 pi? But you can see how these black lines are connected. So here, watch this. Okay. All I wanted to show you, after all that, was that just knowing that there are 4 brushes, I see it froze again, didn't it?
Yeah, I think it's
okay, well, in the end, these things collide and they disappear. All right, and I'm sorry I can't show you this in a better way. Let me, since I want to actually get to the talk part, let me rejoin.
Does everything collapse to a point or something like that?
Yeah, it disappears entirely because
right.
One is an index +1 winding and the other is an index 0.
Right.
Sorry, index +1 and index -1, and they annihilate.
Yeah, sure.
Okay. Okay, so let's hope we don't get frozen now.
By the way, how do you fix the sign of the index, plus or minus?
Well, you can't from looking at those pictures. You can, however, do it by rotating the polarizers. And if the cross polarizers, you rotate the 2 of them, and if you rotate them and the black lines move with them, then it's positive. And if the black lines move against them, it's negative.
Right.
Okay. I'll get this. So, what do I want to tell you about? Okay. So what I showed you, right? So the point would be that you have these 2 defects, and you don't know what the winding is here. Is this +1 and this -1, or is this -1 and is this +1? And the point is, you don't actually need to know that they can annihilate. But if you did want to know, what you would do is you have your polarizer and your analyzer, like Renzo asked. Here's the polarizer and analyzer, and you would rotate them. And if the black lines move in the same direction you rotate, then it's positive. And if they move in the opposite direction, it's a negative winding.
Okay.
But, okay. So what I want to show you, though, is I want to talk about defects and how we classify the defects in a liquid crystal. And so this liquid crystal, this pneumatic liquid crystal, which is the basis of the entire liquid crystal display industry, which is a $100 billion a year industry. The pneumatic liquid crystal, what do you have? You have a map from, here's your sample. And here you have I'm going to draw here the circle. So this would be a vector field, right? This is a two-dimensional vector field. And you have a map from every point in the sample to some element of S1. All right, and we call this the ground state manifold, because those are all the different ground states that you could possibly have. And if it's all smooth, then you don't have a problem. However, it's possible that you have a situation where you take some loop, you do a measuring loop here, and when you do the measuring loop in the sample, it actually winds around. Maybe it winds around twice the circle. So when you look at the image of this loop over here in the ground state manifold, you discover that it maps to a non-trivial winding on the circle. And then you say, oh, is that bad? Well, it's kind of bad, because if you take this blue loop and shrink it to a point, eventually this blue loop, if everything were smooth inside, would map to precisely this point here, would map to precisely one point on the circle. And then you wouldn't have any winding. So it must be that either the winding of the original loop was zero, or there must be a singularity somewhere in there, and the thing doesn't transform smoothly. Somewhere you go across a singularity. So one of the neat things about liquid crystals is that while here you understand what I'm doing is I'm looking at maps from the circle. This circle is the pi1 to this circle, which is the ground state manifold. When you look at maps from S1 to S1, you can do that completely abstractly, and you don't need to worry about what this circle, where these circles live. But in a liquid crystal, the nice thing is that here you have your sample, and this circle, the one that corresponds to the 1 in pi1, actually encloses a region. And this region has material in it also. So in fact, what liquid crystals do is they give you an opportunity to study, if you like, the topology extrinsically. So you can see what's happening in the sample, and you can deduce that there must be singularities inside. And those are the topological defects that I showed you. So you can talk about vector fields, and you can talk about their index. You can also talk about three-dimensional vector fields. Three-dimensional vector fields. In that case, we know that pi1 of S2 is 0. And so you say, oh, 3D vector fields aren't very interesting. Why do I say S2? Because S2 is the space of all the unit vectors, right? Like so, that live on the 2-sphere. That's 0, but fortunately, pi2 of S2 isn't 0. It's the integers. And because of that, it means that if you have a sample, like so, you could actually have a point defect, and you surround the point defect with a measuring sphere. That's this S2, and it gives you a map from this S2 to this S2. And you can classify those, and those are called point defects in a 3D sample. The classic one is the so-called hedgehog, where all the vectors point out. Right? So you could have the one where all the vectors are pointing out in every direction, like so, and people call that the hedgehog. Okay. So there you go. The way you classify defects in liquid crystals in ordered media is you say how do you do it? You say there's a ground state manifold. In this case, it was the circle or the 2-sphere. And if that's the ground state manifold, then you look at maps from the sample to the ground state manifold, and you discover that sometimes those maps have singularities. And the singularities are completely classified by the fundamental group or the other homotopy groups of the ground state manifold. Okay, in fact, it may not surprise you. Of course, liquid crystals, since they have this vector direction, or there's a direction in space, there's even a pi3. They can even enjoy Hopf textures, which aren't singular at all in the 3 dimensions, but still have something interesting. So you can start classifying the liquid crystals in terms of these homotopy groups. Now, that's good. Pneumatics aren't quite like this, right? A pneumatic is a line field, because the molecules have this up-down symmetry, which means that the ground state manifold is RP1 for 2D, and it's RP2 for 3D. And so you see the 3D case is really quite nice, because in the three-dimensional case, we have pi 1 of RP2 is Z2. We have pi 2 of RP2 is Z. And we even have pi 3 of RP2 is Z. So it's kind of nice. In fact, this one system, this one pneumatic liquid crystal system, actually allows you to have a system. I say this is why topology needs liquid crystals, because you actually have a physical realization of something that can have all three homotopy groups be non-trivial. And they can act on each other. So that is what I want to tell you about. This is the old story. The old story that was, promoted by Kamien and Ponaru and Toulouse. But here's the thing: I want to study a slightly different system. I want to study a thing called a smectic. And smectics are different kinds of liquid crystals. A smectic is a system where you have layers. Right? So what happens is on each layer, the layers are spaced apart, maybe some distance A. Oops, I don't know why I called that one D. Some distance A. The molecules are free to move. They're free to move, just like in the pneumatic. And I should have said that. In the pneumatic, the molecules all point in the same direction, but they don't have to sit in any particular place. They can be sit randomly like in a liquid. In a smectic, they have to sit on these layers, but in the layers, they're free to move. They can move any way they like. There's no density correlation. So it's like you have a big building, an office building, and the people on every floor, if you ask me where is the center of mass of the people, you would discover that the center of mass of the people was striated, right? It would depend on, there'd be some people on the ground floor and some on the first floor and some on the second floor and so forth. But you would discover that their locations within the planes, within the floors, were random. And so if you looked over time and said, how do people behave? What is the people density correlation function in a building? It would be a smectic. The molecules themselves, which are still these rod-like molecules, they all align with the normal to the layers. So this is the layer normal. So they're made of the pneumatic liquid crystals, but then they condense and they become something that's a little more crystalline. So it's like a crystal. Okay. So let me do this in 2 dimensions. 2-dimensional smectic. So 2-dimensional smectic, here's the ground state. Okay, the ground state. I can shift the ground state up and down. If this is A, I can shift it up and down. Shifting by A gives me back the same ground state. See, it looks exactly the same. Also, I can rotate the ground state. And if I rotate it by pi, look, it looks the same also. Because I've just turned it over, right? If I rotate it by pi over 2, it looks like this. So I can go like this. So in fact, this 2D smectic ground state, right? These are all the possible ground states. I can take my smectic, I can have it sit somewhere, or I can shift it. Once I shift it an entire distance A, it's the same ground state. I can also rotate it. And when I rotate it, I can rotate it, and once I rotate it by pi, I get back the same ground state. And you say, Why is that interesting? Well, that describes all the ground states. In a nematic, if all the molecules want to point the same direction, then in a nematic, all the ground states are defined by the possible directions in space. The ground state is they all point the same way, and then you say, okay, the ground state manifold is all the possible circles. So the ground state manifold of the Smectic is interesting in this way, right? In fact, you could draw it if you like drawing ground states. So here's the shift direction, and here's the rotation direction. If I shift by A, I get back to where I started. If I rotate by pi, I get back to where I started. These points are all identified. However, notice that if you shift and then rotate, so if I shift, say I go here, and then I rotate by pi, that's the same thing as having shifted in the other direction. These 2 points are identified. And if I shifted by this much, it would be like shifting like this much after rotating by pi. Shifting and rotating is different than rotating and shifting, right? And the order matters. That's because the Euclidean group is, a semi-direct product. The rotations act on the shifts. And so what that means is that if I try to look at the topology of the ground state manifold, in fact, the ground state manifold's a coin bottle. Something that was pointed out to me a very long time ago by Hans Reiner Tribin. Okay, and that's interesting that it's a coin bottle. And again, that's a nice example of why topology needs liquid crystals, because here you have again a physically realized thing that has the coin bottle topology. But that's not what I want to show you. What I want to show you is a theorem due to Ponaru, which I think it was 1979. But there are people on the call who probably know for sure. It was either 1979 or 1981. I can't remember which one. In any event, the theorem is that if you have a Smectic, then you can have a defect in a Smectic that looks like this. You can have a defect in a Smectic that looks like this. You can have one that looks this. You can have one that looks like this. These are the layers. Right? In other words, here, if I draw these are the molecule layers, these is the orientation of the molecules. So if I look at the winding of the 0, here I get plus 2 pi. Here I get plus pi. That's allowed because up and down are the same on a Smectic. Here I get 0. Here I get minus pi, minus 2 pi, minus 3 pi. I can keep going. Minus 4 pi and so forth. But you can go like this as much as you like. You can have any negative charge, but Ponaru's theorem is you can't keep going this way. There's nothing that has winding bigger than 2 pi. So, how does Ponaru prove this theorem? He proved it in some way. It was very hard for us to understand. And I should say this goes back to work with Gareth Alexander and Brian Chen. Well, let me prove to you in a very simple way that this has to be true. Ponaru recognized the fact that these things here, a Smectic, is equivalent to a measured foliation as defined by Thurston. And the idea in a measured foliation is once 2 layers don't touch, they never touch. Right? Everywhere you go in space, you can always smoothly deform space to make it look like they just are nice uniformly spaced layers, like this. There are singularities. The foliations can have singularities where the dimension of the foliation changes, but even then, it's still the case that once 2 layers don't touch, they never touch. So, having this in mind, let me prove to you that you can't have winding that's bigger than 2 pi. So, here I have a bunch of lines, right? So this is my measured foliation. This is my singularity. All of these lines have the same, all of these lines are the same layer. They're all the same layer. Right? So for instance, in this case up here, all of these are the same layer. So these are all the same layer. And then what I do is I say, okay, here's my smectic. The molecule is oriented like this. Like this. I don't know why it changed color. Weird. Okay, like this. Oh, because I have the tutti frutti color. So the molecules rotate by some angle. They rotate by some angle, which is alpha. Right? They rotate by alpha. And then there's minus pi. So this angle is alpha. How much do the molecules rotate? Well, they rotate backwards. They don't rotate just alpha. They rotate by alpha minus pi because they turn over as they go from the bottom to the top. And then I have some, I'll call this alpha 1 minus pi, and this is alpha 2 minus pi, and this is alpha 3 minus pi, alpha 4 minus pi. So if you look at the total rotation, what do you get? When you do the total rotation, you get the sum on the alpha i's minus pi. Well, the sum on the alpha i's, the first term is 2 pi, and the second term is n pi, where n counts how many lines there are. 1, 2, 3, 4, 5, n. So the winding is 2 pi times 1 minus n on 2. Right? So if you have a defect in your singular measured foliation, the winding is 2 pi times 1 minus n over 2. But n has to be greater than or equal to 0. You have to have some line come out. This is the case n equals 0. This is n equals 1. This is n equals 2. This is n equals 3, and so forth. Since n can't be negative, this means that the winding has to be greater than or equal to... the winding has to be less than or equal to 2 pi. And that's Ponar's theorem. But let me say it in a way, yes?
When you talk about rotation, do you mean you go through planes, through layers, or not? You stay in the same layer?
Stay on the same layer.
Right.
Exactly.
Okay.
These are all the same layer, right? All of these are the same layer.
Thanks.
So let me say it in a way that I can understand and which I can generalize. Another way of stating Ponar's theorem is to say, look, suppose I have this, and I have this. And you say, why am I drawing the bullseye twice? Because the bullseye is two different bullseyes. This is the bullseye where all the molecules point out. This is the bullseye where all the molecules point in. Okay? So if I ignore for a second the fact that they live on RP1 and just think of them as vector fields, I talk about this one. This one is a vector field like this. In other words, this has a Morse index of 0. This is like being at the top of a mountain. If I think of this as a topographical map, this has a Morse index of 1, and this has a Morse index of 2. Okay, so that's the Morse index. I can also write down the winding number. The winding number is +1 here, it's -1 here, and it's +1 here. Of course, it had to be that way, because I know that if I take something with Morse index 0 and Morse index 1, I can annihilate them. And if I can annihilate them, I can also make the charge 0. Likewise, if I take an index 1 and index 2, I can annihilate. So then what does Ponar's theorem tell me? There's no way to hook together the 0 and the 2. If you put a mountain on top of a mountain, you still get a mountain. Or if you put a lake at the bottom of a lake, it's just a deeper lake, but it's still a lake. In other words, the only things you can only join together saddles. Right? So here you have a saddle. You can add to it another saddle. Okay, so here's one defect, here's another one. You can combine that until you get something like this. And you can check that the charges work out, right? Here you had n equals 4, and here you had n equals 4 m. So the charge here, this charge was 1 minus 2. This was 1 minus 2. So Q1 plus Q2 was minus 2. Now you have here n equals 6. So Q total is 1 minus 3. So it's minus 2. The charges are conserved. So the reason that you can have any negative charge you like is that you can add saddles together. There's no way to add the mountaintops or the lake bottoms together. Those are the top and the bottom forms. You can't add them, but you can add as many negative ones as you like. You'd get a weird Morse function that has some singularity that's not smooth, but that's okay, right? From my point of view, that's okay. I know it's not a nice Morse function. You could always tilt it to resolve it into multiple defects. And who cares? Well, I already talked about 3 dimensions for you. So Ponaro's result was for 2 dimensions. And the thing about Ponaro's result in 2 dimensions is this tells you something kind of shocking. Does anyone know what the shocking thing is it tells you? Ponaro is shocking. See, I started by explaining to you how topological defects work. You had elements of pi1 of S1, or in the nematic pi1 of RP1, like so. These are both Z. And just like zeros in a vector field, you can add the defects together, right? Not only is this a set, it's a group. And there has to be a way of multiplying and combining group elements. So that meant that if I had 2 plus 1 defects living in pi1 of RP1 or pi1 of S1, I should be able to combine them into a plus 2 defect. In other words, if I had some element G1, G1 squared must be G2, where this is the winding number. That's how it works for vector fields in 2 dimensions. It's how it works for line fields too. But what's so shocking about Ponaro's result? Ponaro's result is saying when you have this extra order, this layering, when you have these measured foliations, when you have layering, this isn't true, right? Layering destroys this. Even though you might have been happy to describe everything in terms of homotopy groups, it turns out using the homotopy group fails. Using the fundamental group fails because the fundamental group does not account for the fact that you can't always add the things together. So you have to do something different. You have to classify them a different way. And so you sort of start to classify them using this Morse index, along with their winding number. So let me do 3D. 3D is super fast now. 3D. In 3 dimensions, do I have the same problem? No. In fact, in 3 dimensions, when I have layered systems, what do the Morse singularities look like, or the Morse critical points look like? Well, here I can have concentric spheres. Like so. Here, I'm thinking that all the molecules are pointing out. The hedgehog. I can also have something just like it. Over here, concentric spheres. But in this case, all the molecules are pointing in. In between, I have 2 other kinds of configurations. Here I can have a cone. In the cone, I'm going to have it be that the molecules point out in the xy plane and then point in as they come in from the top and the bottom along Z. This is a saddle. I can't draw the surface up in 4 dimensions, but you can see it. This is a critical point, which has Morse index. This has Morse index 0. This has Morse index 1. This has Morse index 3. And there's one in between, right? There's another saddle. It looks just like the other saddle, geometrically. But in fact, it's not the same geometrically, because now all the molecules point in the xy plane, and they point out along the z-axis. And this has Morse index 2. So, from pure thought now, you can ask, what is the winding pi2 S2? Right? Pi2 of S2 is how I classified point defects in the nematic. How do I classify them in the Smectic? Well, this obviously has +1. This is the hedgehog, right? It covers 4 pi on the ground state manifold, so it has winding +1. The saddle must have winding -1. Why? Because I can cancel the saddle with the hedgehog. And I know they cancel. I know I can remove them entirely from the system smoothly, just using their Morse index. Likewise, this has to have charge +1, and this has to have charge -1. So you see now, I have 2 kinds of saddles. I still have this thing. This is the top form. This is the bottom form. So I can't add top forms to top forms or bottom forms to bottom forms, but I can add saddles arbitrarily. So I can add the saddles arbitrarily. I can add them, and I can get any charge I like. So now you're happy because you say, oh, so pi2 of S2 does a good job because it now classifies all the defects. But now there's a new problem. There's more than one way to add the saddles together. And in fact, if you try to add the saddles together, you discover that adding the saddles together in different orders gives you different topologies that have the same value of pi2 of S2. They're in the same homotopy class. So if you just look at the arrows, or you just look at the line field, pi2 of S2 is the same, but insisting that it stays a measured foliation the whole time makes that impossible. So you can't transform from one to the other. They're all stuck in the same, they're different from each other. Let me explain how this works. And let me explain how this actually requires some extra thing, an extra physical thing that we didn't have before. So imagine you have a situation where you have here, this is a +1 defect, or -1 defect, back in 2 dimensions. Here's another -1 defect in 2 dimensions. And I want to bring them together. Now, it's one thing if they happen to be attached. I know how to bring them together when they're attached. We'd call this longitudinal adding of defects. But they don't have to be attached. This could be on one layer. I could call this layer phi equals 0. And this could be another layer, phi equals 1. And if I need to bring them together, how do I bring them together when they're on different layers? Remember, it's when you have a measured foliation, you have different layers, right? So this could be phi equals 0, and this could be the level set phi equals 1, and this could be phi equals 2. How do you bring them together? Well, in between phi, what is phi? What are these layers? These are the maxima of where the people are on the floors in the building or where the molecules sit. In between the maxima, there are always minima. So there's another line here. If this is, say, phi equals 0 and this is phi equals 1, there's necessarily in between the layer phi equals a half, right? That tells me, oh, that's the minimum. If I want to bring these 2 defects together, this one and this one, I am forced, so I'll streamline them so that they can go like this. I am forced to take this intermediate layer, like so, and break it into two. Then I can connect these. So there's a move. There's a move which is you have two layers. You have the layer in between. These are max. This is a min. And you convert that to so back here, the charge was 0. But here the charge is 0 also, because here these two have charge minus 1/2, and these two have charge plus 1/2. But you see, it's crazy because one of them sit on the minima and one sit on the maxima. The charge now, the defects are living in different places on the smectic. They're not always sitting at the maxima or the minima anymore. This is what makes the smectic harder to move and harder to make changes on, but it also now implies that I have to have half charge defects. In other words, even if I started with something that was completely oriented, if I want to be able to combine defects in any interesting way, then I have to actually impose extra half-charge defects. Right? These are the important ones. The same is true in 3 dimensions. If I try to take some cone-like piece, right? So maybe there's 2 concentric cones, and here's another set of concentric cones like so, and I try to bring them together, I'll discover that I have to have a surface in here, right? So this, again, this is phi equals 0, and this is phi equals 1, and this is the half layer in between. You have to bring these two together, you actually have to poke a hole in the surface. You have to make a line defect. Can anybody tell me what a line defect is in a smectic? Anybody? Remember, pi1 of RP2 is Z. So in a smectic, you can have line defects. Smectics enjoy line defects. The line defects are precisely the places where the orientation of the molecule switches sign, where it's really a line field. So if I try to orient it, I discover that I can't orient it. And so there's a defect right here. Right? Everywhere else, since it's really a line field, I can put 2-headed arrows on, but still at this particular place, I can't actually define a direction. There must be a singularity. So, again, if I want to be able to combine defects in 3D, I am forced to have these non-orientable defects as well. So even if you start with everything orientable, you discover to have something interesting has to be non-orientable. So what's the whole story here, right? The whole story is that to classify these defects, what we do is we say, here's a singularity, like so. It may have a bunch of cones coming off of it. It could be the boring one, which is just, concentric spheres. So. And what you do is you intersect this point with a sphere, like so, and then you look at the sphere. Here's the sphere. And the intersection of all these cones with the sphere is a bunch, oops, I didn't want that color. There's a bunch of circles. Right, so this is the intersection of those 3 cones. And what you then say is that the way that you describe the different defects, or describe the defect structure inside or at this point here, is you look at the pattern of circles on the surface of the sphere. And I could add, for instance, if I added, I could add another cone like this, in which case I would get an extra circle here in between. So what you get is you get your sphere, so, and it has a bunch of circles. They can be concentric circles, there can be extra circles like this, there can be circles inside those circles, and so forth. And you're talking about now paths or regions on the sphere. And these can all be classified by tree diagrams. What you do is you put a disk. This disk corresponds to a region. So for instance, it could be this one. Then you draw a line. The line is the boundary, like so. Then you draw the other regions that it's attached to. So here's this region, like here. That's this region here. And now this region splits into lots of different pieces. This region has a connection with this region. It has a connection with this region. Sorry, these should be red. This region, and this region. In other words, this region here connects with this region, and this region. And so each of those then gets its own diagram like so. If I take this one, it has one more region, as one more central region like so. So this one here has nothing. That's this one. This one here, if I finish it, has two more regions attached to it. So here's this tree diagram. Like so, here's the tree diagram. How do you calculate the charge of the tree diagram? You say, oh, well, you just take the alternating sum. This is +1, -1, +1, -1. This one is -1. This one is -1. This one is +1. This one is -1. You just add up all the charges. In other words, the charge is just the sum of the it's the alternating sum of the tree. And you can show this directly by looking at the Euler character of the map. This is in our paper. Right? And so it turns out you can have many things that have the same charge but have a different tree structure. All I need to do, for instance, is take this structure and add 2 points to it. Right? So this is adding 2 extra cones. This is geometrically, topologically, a completely different structure. I can't go from one to the other, but they have exactly the same charge. So in 2 dimensions, Ponaro said the charge is not looking at the pi1 charge did not give you something sensible because you didn't really have a group. Here, in 3 dimensions, we have kind of the opposite situation. Looking at the pi2 charge gives you all the information you need. Looking at the pi2 charge allows you to add defects together, but there's actually a refinement. And the refinement gives you this extra structure. And it's telling you how it is that you put the defects together. So, if I may, because we had some technology problems, I would like to finish with asking you guys a question. So this is our result, that in 3D, looking at the homotopy groups, pi1 and pi2, that's not enough. There's actually more structure. The layered systems actually have a much more complex structure in 3D than in 2D. In 2D, there isn't very much structure. You can't actually get the entire fundamental group. But in 3D, you can get the entire pi2, but even then there's substructure which depends on how you put the defects together. So let's see if I can do this. Let's see if this works. Let's see how stable we are. Okay. Oh yeah, here's my picture of a smectic. I had actual pictures of smectics from Norway. But this is what I wanted to show you. So these defects, right? These defects are defects in some system that has layers, right? And I remember Randall and Renzo and Gareth were all at this conference that we had, 1,000 years ago, right, in Santa Barbara. So you have these knots. Suppose that I have a defect that's a trefoil knot. Oops. Suppose I have a defect that's a trefoil knot. Well, the trefoil knot can be fibered, right? This is a knot that can be fibered. The figure 8 knot, I could have a defect that's a figure 8 knot. That can be fibered. But this can't be. No. So what happens? Can you see me? You can see me. Zoom in on me now. Here I have my rope trick rope. So you have a one twist knot, right? There's the trefoil knot for you. Okay? And the trefoil knot, oh, do you see me?
Yep.
Okay. The trefoil knot, right? The trefoil knot can be fibered. And then I can undo it, and I can make the two twist knot, like so. And in the two twist knot, I have the figure 8 knot, and that can be fibered. But the thing that bugs me, because I'm a physicist, and here's the sloppy part we were talking about before the session started. If I make a 3 twist knot, suddenly this can't be fibered. But I can go from a 3 twist knot to a 2 twist knot just by doing that, right? I can make a change that's local. So as a physicist, I would say, how is it possible that this can be fibered and this can't be? Right? This is a fiber knot. This can have layers coming off of it. Those smectic layers all coming off of it. This can have smectic layers. But this can't. And there's an obstruction. Now I know, and you already answered the question, there's some homology, there's some character I can calculate that tells me there's an obstruction, that it can't be fibered, and it has something to do with the cyclic covering space of this knot. But the weird thing is that if I actually try to do it in a physics experiment, it has to be that there's going to be an obstruction. What I would imagine is holding the fibration fixed, the fibered knot image, the smectic layers fixed at infinity. And then I make a change locally. And you say you make this change locally, and you then start trying to repair the layers. Right? That's what you would do, right? If you mess something up, you try to fix it locally, and then what you discover is that you had to go out to infinity and you can't fix it. But I don't know what the structure or the geometry of those obstructions are. And I'm asking you, right? I've heard many of you talk about knots, right? And I'd like to know, what does the obstruction look like? I'm not saying, right, I'm going from a fibered knot, I start with a fibered knot, and now I make a change to it that makes it not a fibered knot. And I want to know what the obstruction to the fibering is, and how I can find it, and how I can see it. So I'll leave you with that. Thank you for your attention.
Thank you very much, Randy. Beautiful talk, and I think we have a lot of difficulties to answer this final question. I think anybody. Fiberness is a big problem, and classification on even 5.1 is already non-fibered. Is that correct?
That's correct. That's the stevedore's knot.
Yeah. So
Yeah.
Anybody?
5-2, so it's a twist knot, 5-2. But
5-2, 5-1, 5-1 is the cinquefoil. It's a
right,
torus knot, so it can be
right.
fibered. Okay.
So do these things have non-finitely generated homology or something somewhere? I mean, these other guys?
Well, that's what you mean, the unfibered knots.
Yes.
Yes, but that just tells me that I can't. I know then that I can't fix it globally. This is what I think happens personally. Okay, what I think happens, if you know, there's Stallings. Stallings had a construction of all fibered knots, and in Stallings' construction
Right.
of all fibered knots, he said, if you give me a knot or a link, you give me a link that isn't fibered, I can always fix it by adding one closed loop. Right? One, I can add the unknot to that link, and it has to, weave through the link, and then I can fix it and make it fibered. So what I think happens is that if you try to take say a 5 the 5-2 knot, the stevedores knot, right, which is the 4-twist knot, and you try to fiber it, you will discover that you have to add a circle. There'll be a new defect, a new singularity, which is a line, right? And this line is going to force you to have some new singularity on there, a new part of the spine of the book that you need to decompose the thing. And it's nice because that means it's local. It means that whatever has to happen, that new loop has to be attached to the link that you were trying to fix, or the knot that you were trying to fix. So that would have a nice physics explanation too. Also, as you know, every knot can be fibered in some 3-manifold, right? And so the only difference between S3 and some other 3-manifold is the handle. And it must mean then that the knot, part of the knot has to go through the handle. If the whole knot can stay inside the big ball part of the S3 with handles, then you don't have a problem. It must mean that the knot has to go through one of those handles. But again, that's circumstantial evidence, right? That's not real evidence, right? What I'd like to know or see is how to explicitly do the construction, right? So if you like, there's some boardism. You have the 3-twist knot, and you have the 4-twist knot, and their boundaries are something. But I'm not just looking at the knots, I'm looking at the fibrations of the knots also. So I have to connect one to the other. And then there'll be some hole, there'll be some place somewhere in the very high dimensional space where I guess it's a 4-dimensional space where I go from the 3-twist knot to the 4-twist knot. In between, I'm going to find that there has to be a new singularity in that space. I just wanted to say, you have these layered systems, and when you're trying to put the defects in, you can be point singularities and line singularities, and I don't even know what kind are the obstructions to actually doing the fibration. Was that answering your question to it?
No, but that is a good question, is exactly what is the obstruction, the geometry of it? I don't know.
Yeah, but I suspect that it's a loop because I can always fix it with a loop.
Right.
Right?
And
But if that's true, then go ahead.
And you can think about putting in a little loop like that kind of goes around. It's like changing a crossing.
That's it, exactly.
You can convert, if you do surgery on that little loop, it changes the 5-2 to 4-1. So you'll lose a crossing. So it gets it down in the vibration.
Exactly. So the question is, is that always the obstruction? If it's just a little loop, then I'm happy. And then physics is also saved because it means that whatever you do, it happens locally. Right? Because as you know, when you study fibered knots, right, and you ask, can you fiber this knot? A lot of the time the answer is yes, because you could fiber this other knot. what you're doing is you're not taking the old vibration and modifying it. You're using parts of the old vibration and gluing it with some other piece to make a new vibration. You're not keeping the vibration fixed also. Right? The layer, you change the layers, but my layers are real.
Yeah, so you want to do something local.
Exactly.
Interesting.
So
I have a very basic question and another question, if I may. So the very
Sure.
basic question, maybe I leave it later. But first of all, is a way to the Penaro's theorem on measured foliations provides a topological barrier that when you go to pi2s2 are somehow are relaxed, something like this.
Well, so Penaro's result was for 2D,
Yes.
right? And in 2D, the problem is that there's only one kind of saddle. If I look at the index, the Morse index,
Yes.
and so you can only in other words, you can add mountains on top of mountains, just give you taller mountains. If you take two saddles and bring them together, you can get a degenerate saddle. Right, that's not a good Morse function, but is still a degenerate saddle, right, where you have three valleys and three mountains, for instance. And so that I think is the essence of Penaro's two-dimensional result. And then when you go to 3D, you realize, haha, now you can actually, since you have two kinds of saddles, you can add any kind of point charge you like. But then you sort of get the opposite mistake, right, which is now the point charge isn't enough. They're not actually homotopic to each other.
Right, and then a very basic question is this: what's the so if you were giving a justification for all this, is that you want defects, you want to classify defects. What's the purpose to classify defects, as physically speaking or technologically speaking? You want a medium that.
Well, yeah. So for instance, you can do experiments. So you can look at the defects, like in those pictures I showed at the very beginning. And when you look at the defects, you can say, oh, without knowing anything else, without being able to see the molecules, I can reconstruct up to homotopy the entire texture just by looking at the points. The problem is that in 3 dimensions, that becomes more difficult because pi 1 has an action on pi 2. So just knowing that you have point defects isn't enough. So then you can say, oh, well, can I classify them up to, there's 42 different configurations or, some number of configurations. And the reason you would ask that is, can you stabilize them? So if you were trying to make a material or a display or something that relied on the defects, can you make them stable or not? You think that you have 2 defects. Do they collide with each other or do they stay there forever? Can you stabilize them? And there are displays that are based on changing the defects. The important part about those displays is that they don't require energy when you're not switching them, right? The background on your iPad requires energy all the time, right, to do that. So these would be bistable, and they wouldn't require energy in between. So these would be like Kindle displays, except they'd be liquid crystal based.
Thank you. Other questions?
Hey, look, Gareth has a Smectic behind him.
Okay, if no other questions, then thank you very much, Randy. Beautiful talk, very interesting and inspiring. I guess you put 2 hard questions, so hard.
Yeah,
hard
questions
to give
are for you.
Yeah.